Algo que es muy importante compartir, esto nos lo han preguntado mucho, y es, ¿realmente se pueden fabricar piezas de uso final con impresión 3D? Y la respuesta es sí, justamente vamos a ver eso el día de hoy. Te pongo en contexto, vamos a hablar hoy de la tecnología de impresión 3D a grandes rasgos. Vamos a hablar sobre la relevancia que esta tecnología tiene en la industria aeroespacial. Y después tenemos un invitado de lujo que nos va a hablar sobre todo lo que hay alrededor de estos procesos de certificación. De parte de todo el equipo de 3D, te doy la más cordial bienvenida. 3D somos un equipo de especialistas en manufactura aditiva e impresión 3D. Gracias a nuestro joint venture con Stratasys, la empresa de impresión 3D más grande del mundo, podemos acercar a la industria mexicana más de 300 equipos de impresión 3D profesional para fabricar piezas en plásticos, metales, resinas y que cada día esta tecnología sea mucho más conocida. Poniendo en contexto, si es la primera vez que nos acompañas, en el mundo hay tres maneras de fabricar: la tecnología sustractiva, la cual conocemos como torno, fresa, CNC, y todas estas tecnologías que lo que hacen es, a partir de un material, remueven, quitan material y forman la pieza. Normalmente es una tecnología muy utilizada en la industria aeroespacial. La segunda de ellas es la formativa, en la cual pues hay que invertir en un molde y con ese molde podemos fabricar cientos, miles, decenas o millones de piezas para hacer producciones masivas. En la industria aeroespacial también es una manera de formar utilizada. Y recientemente, y decimos recientemente entre comillas, porque la tecnología ya lleva más de 30 años existiendo, pero a partir de hace unos años empezó a tener gran relevancia en la industria aeroespacial, que es la manufactura aditiva. La manufactura aditiva es un conjunto de tecnologías, es una técnica también conocida como impresión 3D, que como funciona es que puedes crear cualquier objeto con base en un modelo 3D de computadora, lo traes a la realidad mediante este tipo de tecnologías, que lo que hacen es, de diferentes maneras, ir depositando una capa de material tras otra hasta formar el objeto que tú diseñaste. Entonces, esta tecnología tiene la característica de poder hacer geometrías muy complejas, puedes hacer piezas en ensambles, muchas piezas impresas en un mismo ensamble. Entonces, tiene muchas bondades la tecnología que tocaremos otro día. Hoy nos vamos a enfocar más en las grandes ventajas que tiene. En la impresión 3D, tú puedes fabricar en diferentes materiales, principalmente termoplásticos, metales o resinas. Para el tema aeroespacial, pues hay materiales plásticos retardantes de flama, otro que se llama Ulte, Mantero, ya estaremos hablando de ellos hoy. En metales hay una gran variedad de metales para fabricar piezas, y las resinas son materiales para hacer piezas de muy alto acabado visual, pero quizá no son las piezas más resistentes en aplicaciones aeroespaciales. ¿Por qué la impresión 3D tiene tanto potencial en la industria aeroespacial? Y la respuesta es porque los bajos volúmenes, la alta mezcla, la alta complejidad de las piezas hacen un fit perfecto con la tecnología de impresión 3D. Vemos ya muchos casos de aplicación, cada día van sonando más, cada día conocemos más. Y es algo muy cierto que el día de hoy la industria que más aplicaciones tiene de impresión 3D reales de piezas y productos finales es la aeroespacial, pero también es la industria que más futuro tiene potencialmente en temas de manufactura. La tecnología hoy en día se utiliza para fabricar prototipos y acelerar mucho procesos de diseño y desarrollo. Se usa mucho, sobre todo en México, en temas de jigs, fixtures, tools, methods, herramientas que permitan al operador en piso de producción hacer su trabajo mucho más rápido, mucho más eficiente y libre de errores. Hay una gran tendencia de fabricar spare parts para temas aeroespaciales, piezas ya obsoletas o piezas complejas de maquinar. Y finalmente, lo que nos trae el día de hoy son piezas de uso final. Para que te des una idea, Airbus, Boeing, cada día integran más piezas impresas en 3D en sus aeronaves. Comenzaron siendo un par de piezas metálicas, hoy hay miles de piezas impresas en 3D dentro de los aviones comerciales que conocemos, tanto al interior como en motores y como componentes relativamente críticos. Entonces, Para hablar de este tema, hoy tenemos a un invitado muy especial. Sevcik es el vicepresidente de la división de la Industria Aeroespacial de Stratasys. Es una persona que lleva 20 años en la industria aeroespacial. Ha trabajado para Lockheed Martin, para la NASA, para UTC Aerospace, y desde hace 6 años ha estado liderando los esfuerzos aeroespaciales de Stratasys. Scott, it's great to have you here.
Hello, Sebastian. Thank you for having me.
It's a great time to have a conversation with you. People is very excited to hear what you have to say, and we are more than happy and ready to hear from you everything around the aerospace production of additive manufacturing parts.
All right. Well, again, thank you for the opportunity to speak with your audience here today. This is a topic that is very exciting for me. It's something that I have been focused on for a long time. 20 years in aerospace, the last 6 years in 3D printing has led me to a place where I have a unique insight, I think, into what's happening around the world with aerospace production with 3D printing. And the two things that I'll start out by saying as I walk through some different examples of both of the parts that are flying as well as how people have gone about certification is first, aerospace production with 3D printing is much further than anybody is aware. There's a lot of discussion around a handful of metal parts that have made a lot of news, brought a lot of attention because they are going into aircraft engines. But beyond that handful of metal parts, there are literally hundreds of thousands of polymer parts flying in aircraft today. If you've flown on an A350, there are printed parts on that aircraft with the FDM technology. If you've flown on a 787, there were printed parts on that vehicle with the SLS technology. These parts are very present already in aircraft, and we're seeing more and more interest, particularly in the aftermarket, in spares, in bringing additive manufacturing into the production processes that are in use. And in addition to that, in addition to aerospace production being much further than most people are aware, the other really interesting point to know and to understand is that 3D printing is not treated uniquely. It is not qualified or certified in a way different than any other technology. There are differences without a doubt, and those differences come from the fact that 3D printing is a new technology. So there isn't the body of evidence, there isn't the handbook information available to make qualification processes and certification processes easy. So what I'll talk to today is how that gap has been overcome by many of our early adopters as they've taken the FDM technology in particular into flight qualified applications.
That sounds great. Y para todos los que nos están acompañando, recuerden que en la sección del webinar de preguntas pueden ir escribiendo todas las preguntas que tengan y al final Scott y su servidor las estaremos contestando. Scott, the audience is yours.
Very good, thank you. I will start by going into some examples so that you can see some of the ways the FDM technology is being used in aircraft today. One of my favorite is this picture, and this is one of the first. Back in 2013, Airbus was looking at 3D printing technologies, understood the material Ultim 9085, which is a high-performance thermoplastic that has been used heavily in injection molding and was originally developed by GE Aviation specifically for aircraft interior requirements. So Airbus looked at the fact that this material could be printed and saw long-term the benefits that that could bring. They took the opportunity that you see on this screen to test whether or not a part could be certified. So this is a part that is on a flight attendant seat on an A310 aircraft. So it's an older aircraft, or an aircraft that didn't have much time left in service, and it was a single part, very low volume. So they looked at whether or not they could print the part rather than sourcing a new replacement part, because their original supplier was no longer in business. The tooling design information was lost, so they'd be starting from scratch for one part. This could have been a very, very expensive seat component, but instead it became an opportunity for Airbus to prove the technology had a place within aerospace. That was in 2013. By the end of 2014, Airbus had conducted a qualification and had included specifications, both a material specification and a process specification, within their type certification package for the A350 aircraft. When the first several A350s were delivered at the end of 2014, there were about 1,100 printed parts across those first 3 vehicles. The parts that were printed were not the primary part on the bill of materials. They were not selected for lightweighting or for other values that you typically see with additive manufacturing. They were parts like this, very simple parts that were either injection molded or stamped metal parts, but those parts had changed late in the design cycle and were unavailable at the time that they were needed. Rather than let trivial parts like these delay delivery of an aircraft, Airbus had worked in parallel to qualify the technology so that they could put printed versions of these same parts on the vehicle as alternates. So these parts were originally referred to as missed part production and were alternates on the bill of materials with the intent of, at the aircraft's first C-check or first major MRO servicing, it would be replaced with the primary part. This was very, very successful for Airbus. Airbus learned the production process. They had developed suppliers. They had developed specifications, and they recognized that missed part production was definitely of value, but they could go much further. So going beyond that missed part production, the first few aircraft, they proceeded to identify parts that would buy their way onto the aircraft, parts that would replace a traditionally manufactured part and become the primary part on the bill of materials. Initially, that was about 3 dozen or so parts that were identified early in the A350 program. Those 3 dozen or so parts had multiple instances on aircraft, so very quickly there were hundreds of parts being delivered on each A350. This gave the organization more and more comfort with the technology. It gave their regulators, their certifiers, more comfort that the technology could be used within an aerospace context. And it gave the designers more understanding of what could actually be done with the technology. That's led to more modern parts on Airbus aircraft, such as this one. This is a cosmetic part. We're actually looking at the back side of this, but it's a spacer panel that goes in A321 aircraft for Finnair in Europe. There were only a few of these needed per aircraft, so it was going to be a challenging and expensive part to tool for. But they had the technology, they had additive manufacturing, they had the right material, so they could produce these parts in a low volume fashion very cost effectively. What you see in this part as well is, unlike those last parts that were clearly not designed for additive manufacturing, the designers are now able to really take advantage of some of the core values of design freedom. So this part is 15% lighter than the part that would have been produced if additive manufacturing wasn't available. And you can see that in the design that you couldn't tool for this part. This could not be an injection molded part. It has to be additively manufactured. So that is the state of design now at Airbus, where these components such as this for custom interior configurations, and to a much greater extent, more and more opportunities to implement additive within the aftermarket, within their spare part production, are taking hold and finally utilizing the technology to its extent, not just for its supply chain benefits, but for its design benefits as well. So this is at an OEM, this is at an airframer, to some extent now with their aftermarket arm Satair as well. We've also seen operators using the technology in the aftermarket for some of the same benefits. So this is one example at China Eastern. They created a iPad holder, iPad mount for their electronic flight bag technology to consistently mount in cabins of different aircraft. So they have a common interface, whether a pilot is stepping on to a 737 or if they're also rated for an A320, the same interface exists for them to mount their iPad. Even more exciting for me than this specific example is what they're doing in the back of the aircraft. I don't have a picture to share on this one, but one of the parts that very commonly breaks in a China Eastern cabin configuration happens to be a newspaper holder, a small curved piece that sits on the front of a business class seat module. It's frequently kicked, not well supported, breaks constantly. So they were continuously ordering more and more of these parts. They struggled with lead time, they struggled with consistency. They determined that they could print them themselves internally, avoid lead time entirely, and actually produce the same part at a much lower cost. So examples like this are early, I would say, in aftermarket, but they are becoming more common as the technology becomes more understood, becomes more repeatable, which is key, and starts to meet some of the other traditional requirements that you see within aerospace production. And that's a topic I'll come back to in a few minutes. Very similar in the aftermarket is this example. So the US Air Force has an old fleet of planes. Their transport aircraft in particular, the C-5 and C-17 are both out of production. C-5s haven't been manufactured in 30 years. They're still producing C-130s, but the big aircraft, the workhorse aircraft within the Air Force, are being maintained as out of production aircraft. These parts that you see on the screen, this is actually an aircraft lavatory panel. So a part for the lavatory on board the aircraft that is a difficult piece to maintain. Painted parts tend to show corrosion, degradation. So they asked us if we could produce a colored material for them so they could just print this part and put it on the aircraft. That's exactly what we did. This part is now flying, as well as several other parts flying on C-5s and C-17 aircraft. The Air Force, once they recognized a certain level of maturity within the technology, began to prepare their documentation, their specifications and procedures for utilizing the technology in-house. This has given the Air Force a lot of flexibility. Where they can go to a supplier, they do go to a supplier. Where they can't, or where they have an urgent need, they now have capability in-house that they have confidence in, they have trained operators for, and they can move forward with producing their own spares when it is the scenario that meets their needs best. This isn't from an aircraft, but rather from a launch vehicle. This is a duct that is on the Atlas V rocket produced by United Launch Alliance. Before this ducting system was printed, it was a metal system. There were 140 different pieces of aluminum that were involved in the assembly. A lot of this was components simply for fastening other components together. ULA was able to go from 140 pieces of aluminum to 16 pieces of plastic. So an order of magnitude reduction in part count. That also allowed them to stop procuring the parts entirely. They brought this production in-house. They now produce their own ducting, have complete control over timelines and quality requirements. So whereas some organizations like Airbus predominantly outsource and look to build up their supply chain, other organizations are using this as an opportunity to insource. What's interesting is that still ends up driving them to suppliers who can meet their needs as well, because they very quickly become overloaded with their own internal capacity and need additional support from industry. So in addition to the massive part count and the values that they find in insourcing, this is also a significant cost savings, almost 60% in terms of cost savings. And that's through reducing assembly labor, reducing procurement costs, and reducing risk of not having components when and where needed. Another great little component is this pressure regulator bracket. We've been working with a company called Boom Supersonic. Boom is producing a new supersonic transport aircraft. They're building their demonstration vehicle now. They'll then move to approximately a 50-passenger passenger jet intended to replace many of the Concorde's old routes. So travel over the ocean to avoid sonic boom considerations. But what has been really exciting and interesting for us and a great opportunity is they're starting from scratch. It's a clean sheet aircraft design. Whereas on United Launch Alliance, that's an existing rocket. It had qualified ducting. the additive ducting had to be traded against that qualified system. It had to qualify a new technology. It had to be an overwhelming opportunity. Boom isn't trading against existing parts. In some cases, they have an opportunity to use an existing part from a different aircraft, but a lot of the gaps need to be filled with new parts, and a new technology at their disposal is a phenomenal entry point for them. So this is a pressure regulator bracket. This holds a small component to the skin of the aircraft. They only need a couple of these for their demonstration aircraft. So the lead time of taking 6 weeks to request a part like this and to get it in-house doesn't fit with how fast this company is moving. The ability to print it in an afternoon absolutely does. So this is the kind of low volume manufacturer that really is an ideal fit for additive. Boom's taking advantage of some design freedom here as well, building a more complex part because they can, but what made this part get on the aircraft is the fact that they could get the part they needed almost immediately. When we look through what Boom is doing, the opportunities are incredible, and they have done a wonderful job sharing online the build of their aircraft. And one of the most exciting things for me as they do this is being able to watch and see the various ways that they're using additive. They do a tremendous amount of tooling, certainly, and they've been sharing much of that online. In fact, drill blocks are a tremendous application for them, and I would be surprised to learn that there are any holes on their XB1 demonstration aircraft that weren't drilled through a 3D printed drill block. But these are the kinds of things, these are the kinds of opportunities that they very quickly found on the aircraft. So just looking closer at some of these, simple pieces like a pass-through component here, protecting the cable here from the bulkhead, and at the same time, this is all composite, so protecting the composite from the cable. Ducting, as you saw with United Launch Lines, ducting tends to be a tremendous application because it is frequently a very odd geometry. It's frequently designed last and having to conform to other equipment, other structure that's already in place. And then you can see some of the other examples on the slide here as well, like this. They've got a conduit routing through the fuselage that has a number of different turns and different offsets from the surface. So the ability to make each one of these parts unique and fit for purpose exactly where that part is going to go is a tremendous benefit for them to move quickly again, and also ideally from a cost standpoint, low volume manufacturer. But this is where we hope they'll go, and this is where we see a number of airline and airframer customers go as well. There's a tremendous push, and even though commercial aerospace will take a step back now for a couple of years as we rebuild the demand post-pandemic, there is a tremendous interest in personalization of aircraft, differentiation of passenger experience. So the ability to take a higher mix in manufacturing, the ability to print one thing today and print another thing tomorrow allows for personalization in an entirely different way. So while this part isn't flying today, when we show a picture like this, it immediately speaks to many of our customers' strongest desires in terms of what they want to do inside of a cabin. Within a business class cabin, being able to do something like this, if you're delivering an aircraft to a specific customer, being able to incorporate their logos, their style into that. With major aircraft OEMs, being able to incorporate the design of the design elements of an airline, or make each aircraft unique, provide that additional personalization experience that has a tremendous amount of value and interest to those airlines. So just a quick summary of the reasons why you see the reduced cost and the higher mix as I talked about. And in the aftermarket, the reduced lead time and the ability to deal with diminishing supply sources and avoiding obsolescence all really drive the interest in adopting additive manufacturing for these different spaces. But that interest is only a starting point. Then it comes down to how are we going to do it? So I'll go through just a couple of adoption journeys, a couple of customers and how they have gone from this is of value to us to these are parts in a vehicle. So Airbus, going back to that example, they're a great example of an early adopter. They took a big risk. There was executive intent. There was a desire to put printed parts on aircraft to prove whether or not the value they saw could be realized. They took a big risk, and it paid off, in my mind, both for Airbus and certainly for Stratasys as well, by identifying the need and identifying an opportunity to prove it out. So they picked one spare part opportunity, selected a technology, and qualified that one part, did a point design certification. They printed a number of these parts, they broke a number of these parts, and they showed to their certifier, their airworthiness authority, EASA, that this part was sufficient for operation on an aircraft. No different than any other point design certification would have been handled with an airworthiness authority. To go beyond that, though, they don't want to, and no one wants to certify every part they put on an aircraft. They want to certify classes of parts. They want to certify to a specification. So that's where they went next. They needed to establish material traceability. They needed to write a material spec and a process specification, then conduct qualification testing so that they could have a body of evidence to provide within their type certification claim. As I said, their initial use then of that specification was for missed parts production. They then proceeded into serial part production as they identified parts that bought their way onto the aircraft. And now they continue to move forward from that, looking for more and more parts, both at OEM and MRO levels, and also starting to explore additional materials, additional technologies to expand the ability for Airbus to meet different application requirements. Similar, but in some ways different, United Launch Alliance started about the same time as Airbus, but they came from a slightly different place. Their vision wasn't, let's go print parts for the vehicle. They had bought a printer. They had, in many ways, overbought a very high capability printer for producing trade show models. They had a young engineer come out of school familiar with our technology, see that capability sitting idle and say, hey, can I produce tools with that system? It was a Fortis 900. After very quickly transforming significant operations with tooling production, a young materials and process engineer recognized the material as a material that could be flight qualified. And she proposed doing just that. So just like Airbus now, they wrote material specifications to establish traceability. They wrote process specifications to establish repeatability. They conducted a qualification to prove that this technology could meet their launch vehicle requirements, and then began identifying those overwhelming business cases where it made sense to replace components on an existing vehicle design within the Atlas V, such as the duct. And that enabled them to then look towards their new vehicle, like Boom, to find the places where a part could be implemented very cost effectively, taking full advantage of the technology, not having to compete with an existing part. Air Force was in a different position. The Air Force was early in testing and evaluating, but they were not about to take the same level of risk that Airbus, frankly, did. So they encouraged the industry to come together, to work together, to provide public specifications, public data, really move towards a specification, or excuse me, a standardization approach. As we were able to do that, as we were able to show with public data the repeatability and performance of the process, then the Air Force was able to write their own documents, bring the technology in-house, and begin to use it for their own sustainment operations. Where we are today, because of the efforts of the early adopters and because of the efforts of the Air Force in driving towards standards, is we have companies like Safran who are able to take now a very balanced approach. Safran started with rapid prototypes and tools, understanding the technology, using the technology, building comfort with FDM. And then they produced a part like you see in that picture. It's a small locker component, and like the ULA duct, it was a significant reduction in part count. They were able to produce this and use it as an example internally as to why they would want to move forward with additive. We worked closely with them, sharing the public data that came out of the activity with the Air Force, and that became a starting point for them. Now they had confidence that they could go into qualification knowing that something good would come of it. Airbus, they took a risk. They didn't know that they were going to get sufficient performance out of the qualification they were performing. Now we have objective evidence so that Safran does. They know that they have a winner when they begin. That, in concert with the fact that Airbus is their customer and they know what Airbus is doing and Airbus is encouraging their supply chain, we have a tremendous set of motivators for a company like Safran to move forward, which they have at this point. And there are others, Deal, UTC, well now Collins, Raytheon, whatever their name is at the moment. All of these companies within the supply chain are moving forward with technologies like this in order to meet the needs that we saw on that earlier slide, or take advantage of all of those values. So we've learned a lot from these interactions as we've been alongside our customers in these various adoption journeys. Some of the key pieces, number one is traceability. It is an entry point. It is a table stakes, you would say. If you cannot prove what your material is, that your material is the same that was used during qualification, then that material will not go on an aircraft. Material and process engineers have become, I would say, our best friends as a technology provider, and our most challenging customers to convince. They are responsible for saying whether or not something is safe on an aircraft. So they are who have to understand that level of traceability to ensure that they have a supply chain just as robust and as consistent as a traditional technology. Lack of repeatability is also a significant a challenge. And as we look across different technologies, and there have been some third-party studies that have looked at this as well, most additive technologies, frankly, today are not repeatable. Stratasys technology, when we started down this path, was not repeatable to the level that is needed to convince customers that they have a technology that they can convince their airworthiness authorities is certifiable. So lack of repeatability means you're not taking full advantage, and I'll show that a little bit further in a slide ahead. And also, and this is to the point I just brought up around Safran, they knew that they would succeed in their qualification. And when you don't, unless you're an Airbus, unless you're a Boeing, it is too expensive to go about qualifying a technology that you don't know will meet your needs in the end. So we address traceability first. It required some changes on our part and other material providers in the industry. I imagine will soon follow suit in being able to provide to their customers fully traceable material in an auditable process. We have our customers come to our facilities to see how we produce material, to verify that we are following our processes. And then with each delivery of material, we're providing not only a certificate of conformance, but also a certificate of analysis where we're documenting all of the properties that they know need to be controlled to ensure that their qualification is not invalidated, to ensure that they are getting the same material with the same performance that they expect and require for flight parts. At Stratasys, these are our certification grade or CG materials. Repeatability, like I said, this is the key to unlocking the potential of the technology. This gets more parts on vehicles. When we started, we had a datasheet value for Ultim 9085 of 6,000 PSI in terms of Z-axis tensile strength. But there was a lot of variability around that number. So our early adopters, like Airbus, needed to be very, very conservative. So they're taking very little advantage of the true capability of the material. When you take a specification, take a spec value knockdown to 4,000 or 4,500 PSI, you're not really taking advantage of the strength of the material, which means you're using a safety factor that prevents you from lightweighting the part that you're looking to. After the work that we've done to improve the repeatability of a Fortis 900, so we now have what we call our AIS configuration of the 900. We have incredible control, incredible repeatability with that process, and that's been part of public testing that has shown not only that the consistency of that part strength is there, but as a result, we have also significantly raised the average value. So from our early adopters, so from where Airbus set their standard to where Safran is able to set their standard is significantly higher. We believe that all suppliers of technologies need to do this. We are proud to be out in front with the Stratasys F900 AIS configuration, but for this technology to really be embraced within the industry, especially by airworthiness authorities, what we need to be able to show is the level of repeatability you see on the right side of that slide, not what you see in the middle. So we worked to improve repeatability. We worked to gain that performance we see on the right side. And we took the encouragement of the US Air Force to make this information available. So we worked with Wichita State University, which hosts the National Institute of Aviation Research, which, and we're going through all of the acronyms, has an office called the National Center for Advanced Material Performance, NCAP. For about 15 years, NCAP has been doing public qualifications of composite material systems. Composites and additive end up having a lot in common because what's unique to composites is your part properties are determined by the process you use. That's exactly the same with additive manufacturing. Some people look at the materials and say, well, these are materials like I would see in injection molding, so I'm going to follow the path of injection molding. It's completely the wrong approach. The process by which composites are qualified, specified, that's the approach that works for additive manufacturing because the process of the materials are so integrally linked and your material properties will be determined by the process in which you use. So that's key, and that's something that we recognized in working with NCAP as using composites as the starting point. So now you can go today, you can search this on Google and end up on the Wichita State University website and download a process specification, material specification, and statistical analysis around what is achievable with Stratasys Ultim 9085 on a F900 AIS package. This is a data set that can be used by other companies to demonstrate equivalency, so they can go and perform a subset of testing with their F900 AIS and Ultim 9085 and use that as evidence for their certification authorities. And we have some customers that are doing that, but more customers are doing exactly what Safran's doing. Seeing this as objective evidence that the process can result in very high performance, and then they are starting with these documents and performing their own qualification, addressing their own needs and their own applications. So this has become a resource of templates, material specifications and process specification templates, as well as that evidence, that statistical report on what can be achieved with the technology. Even the Air Force, after sponsoring this activity, they created their own documentation, their own processes by which they execute printing within their organization. This is also leading directly to an actual standard. So this is qualification information available, but ultimately, just like any other manufacturing technology, standards are the way that we can enable more broad adoption. So there's a standard written today. It's still a work in progress, but it is available through the SAE, the standards, the AMS 7100 family of specifications that rely on the same F900 AIS configuration and Ultim 9085 material, and this same evidence that you see from NCAP to basically lay the groundwork for the first true standard for a additive manufacturing technology. How that all fits together is at Stratasys, we're providing a printer, we're providing the F900, we're providing material, the certification grade Ultim 9085, and we're providing this AIS readiness package, this configuration that takes a good printer, the Stratasys F900, and adds to it process control documentation. Outside of printing, we're controlling material handling, we're controlling moisture, we're advising on how to get the machine into the ideal state of performance, how to ensure that that system is performing at that level in production processes, and providing a toolkit with the tools and able to enable a customer to show that to their certification authority. We're not performing the equivalency. That's something that that happens with NCAP. So just that distinction, we're providing that means of compliance with process documentation, material, and hardware. But the testing still stands aside with the NCAP organization. So that's a little bit about the parts that are flying, the way that our customers have proceeded, and what we've learned in that process, and what we're doing to try and help customers have a better path to flight certification of FDM parts in particular. With that, certainly I am happy to take whatever time, Sebastian, you've got allocated here for any questions I can answer.